Okay, thank you, Ace, for that introduction. I hope you can see, just a minute. I had something on my screen there. I'm trying to change my screen now. Hang on. Yes, have you seen the change of the slide? Good. So the work I'm going to talk about is in collaboration with my old friend Henry, my young friend Andrea, and my new friend Manos, without whom a lot of this would not have been possible. So the timeline for the work starts in 1944 when von Neumann and Morgenstern published the theory of games, which formalized expected utility theory, which incorporates the principle of transitivity of preferences. And mainly, though, I'm going to talk about Amos Tversky's landmark paper, Intransitivity of Preferences. After his study, there are at least 8 replications of one of his studies, the lottery study, and 5 explored the nature of intransitive preferences, including my small scale study and Henry Montgomery's replication, which elicited think aloud protocols, both published in 1977. And Kalenscher et al.'s participants carried out the task in a scanner so that neural responses could be measured. Now, 3 other replications revisited the issue from the point of view of transitive models. Birnbaum and Gutierrez found that very few people repeated intransitive patterns, and Regenwetter et al.'s paper was a major critique of Tversky's work that they called transitivity of preferences. And in the same vein, Cavagnaro and Davis Stover called their paper transitive in our preferences, but transitive in different ways. And recently we reviewed the evidence from the perspective of dimensional models, and our paper was published last year in Decision. And at the moment, we're carrying out some further analysis to evaluate different accounts explaining this data. So as I said, models of decision involving risks, such as the EU model, included transitivity as a basic axiom. Transitivity preferences is if A is preferred to B and B to C, then A is preferred to C. In the 50s and 60s, Ward Edwards and others considered whether there were circumstances in which decision behavior would violate the transitivity of preferences principle. And an influential paper by Kenneth May, where he carried out a pilot experiment, argued that if choice depends on conflicting criteria, that is, if alternatives are compared by dimensions, then preferences may be intransitivity. The transitivity principle may be violated. But it wasn't until Tversky's study in 1969 that there was strong evidence of violations of the transitivity principle. In his paper, his research question is, he addressed a research question by developing theories about how people process decision information and what strategies they use when choosing between multidimensional alternatives. And in particular, do people use dimension-based strategies, and can these lead to intransitive preferences? Although his empirical question was, is weak stochastic transitivity violated? And this is the principle, the rule that if the probability of choosing A over B is greater than or equal to 0.5, and the probability of choosing B over C is greater than or equal to 0.5, then the probability of choosing A over C will be greater than or equal to 0.5. In other words, if people generally prefer A to B and generally prefer B to C, then they will generally prefer A to C. So it's a much weakened version of the transitivity principle. But that's what he tested in his experiment, where he used win-only lotteries, such as these. In lottery A, you can win $5 with a probability of 7 out of 24. Or you can choose lottery B, where you can win a little bit less with a little bit greater probability. So Tversky actually presented the probability information graphically rather than in text. But in my replication, I used text and got the same effects as he did with text probability information. The main dependent variable in these experiments is the choice proportion, the proportion of times lottery A is chosen over lottery B in, say, 10 or so presentations. And this is the set that Tversky used in his original study, where, as you can see, as you go from lottery A to E, the probability of win increases in small increments, and the amount that can be won, the payoff, decreases in small increments, and always the two dimensions that are in conflict. And the transitive pattern would be when A is preferred to B is preferred to C is preferred to D is preferred to E, and A is preferred to E. But an intransitive cycle is when E is preferred to A. And his first model that he developed is the additive difference model. And this is a compensatory model where people are assumed to use all the information available. And they weigh the subjective difference in probabilities, the advantage for the P of the lottery B in the two I've just shown you, against the subjective difference in the payoffs, A's advantage in the payoff dimension. So these are weighed against each other. And in this hypothetical example, the prediction is that when choosing between A and B, generally 80% of the time, preference is for the better payoff. But as the difference between the two lotteries increases on both dimensions, this tendency gradually decreases until when the difference is, say, 50 cents or more, the preference switches to the weighing up of the differences goes in favor of the better payoff, a better probability, so that the choice proportion for the better payoff is below 0.5. So in this situation, if this happens, the prediction is that transitivity, weak stochastic transitivity, will be violated. His other model was the lexicographic semi-order model. This is a heuristic where people aren't assumed to use all the information. It's a shortcut. You choose the better win probability unless the difference in probabilities is below a threshold. And if it is, you choose the better winning amount. So the prediction from this hypothetical example is that above the threshold, you always choose the better probability, but below the threshold, or always or generally, below the threshold, you more generally choose the better payoff. And again, the prediction is that if this strategy is used in this way, in this stochastic way, weak stochastic transitivity will be violated. So it's the same testable consequence as the additive difference model. And Tversky never distinguished between the two. He just tested whether weak stochastic transitivity would be violated. So in his experiment, he presented the lotteries you've just seen in pairs with the probabilities of win as a circle. And in the pretest, 18 Harvard undergraduates were tested for the tendency to choose the better payoff when the differences were small, A over B, but the better probability when the differences were large, i.e. E preferred to A. So 8 of his participants exhibited that pattern, and they took part in the main experiment. And in the main session, 20 replications of all critical pairs were presented with filler trials interspersed. And this is the results from his participant 1. And as you can see, it resembles the pattern, so let me just go back. It resembles the pattern that was predicted by the additive difference model. There's a gradual change as differences increase from preferring the better payoff to preferring the better probability. And he found in his study that 5 of the participants significantly violated weak stochastic transitivity on his likelihood ratio test, which is about 28% of the participants. So Ranyard et al.'s critique had a number of strands of criticism. The first is they argued that weak stochastic transitivity is a poor criterion of stochastic transitivity because, among other reasons, it's confounded with preference variability over time. And they argued that the triangle inequalities condition is a superior criterion of transitivity. This is a triangle inequalities. The probability of choosing A over B plus the probability of choosing B over C minus the probability of choosing A over C will be less than or equal to 1. And if that inequality holds for all triads, then the data is said to satisfy stochastic transitivity in this sense. The second criticism was that when a proper statistical test is applied, Tversky's findings of violations of weak stochastic transitivity and triangle inequalities can be explained by an underlying transitive preference and type 1 error. In other words, instances of violations of transitivity are basically a statistical error, a type 1 error from a transitive model. Cavagnaro and Davis-Stover modified that position, but that was the critique in the 2011 paper. And a third important point they made, or argument they made, was that violations of stochastic transitivity haven't been reliably replicated. Now, when we looked at this critique, we felt that there were some unanswered questions about this evidence. And the first one is, what can be learned from a rigorous exploratory analysis of the data? And previous analyses didn't present any descriptive statistics. Secondly, how well does Tversky's extended additive difference model account for intransitive stochastic choice? And surprisingly, Tversky and subsequently, no one had tested the goodness of fit of the additive difference model. Thirdly, what can be learned from decision process evidence? As I mentioned, there is think aloud data and neural correlates in this task, and the reviews I've mentioned were silent on this this aspect of the evidence. And finally, is evidence of intransitive preferences better explained by compensatory processes or heuristic processes, the additive difference or the LS model? Again, surprisingly, the two accounts haven't previously been compared. So the aim of our study was to review and reanalyze 7 data sets from the perspective of dimensional processing models which allow intransitive preferences, in particular to carry out a rigorous exploratory data analysis, to develop and test the goodness of fit of a 2-parameter simplified additive difference model, and to compare the SAD model to a constant choice probability model, which I'll explain later. And overall, to reevaluate again the replicability of Tversky's findings of systematic and predictable violations of weak stochastic transitivity. So that was the aim of our study. And when we did the exploratory analysis and applied it to Ranyard's data, we found that there were several cases with observed violations of weak stochastic transitivity similar to Tversky's reported cases. And as well, several of the transitive cases in Ranyard's study were consistent with one-dimensional take the best heuristics. So this is Ranyard's participant 12. And as you can see, there's a pattern of changing choice proportion that's very similar to Tversky's participle 1. Here, there is indifference between A and B, but it gradually moves towards a stronger and stronger preference for the better probability. And in the next row, you can see it goes from strongly favouring better payoff to strongly favouring better probability. So on the descriptive statistics, the mean choice proportion is 0.4, and 4 of the choice proportions are outside the confidence interval for constant choice proportion. So that model doesn't appear to fit this data. And as well, if we did a regression of the probability difference predicting the choice proportion, and there's quite a strong negative correlation, so that for every change of 1 dimension difference, there's about 20% change in choice proportion. So quite a strong relationship between probability difference and choice proportion. With another participant 10, you can see here that usually there's a very strong preference for the better probability, so that the mean choice proportion is just 0.07, and nothing's outside that confidence interval for that choice proportion. And there is a relationship between probability difference and choice proportion, but it's rather small. So this kind of exploratory analysis motivated us to actually do some model building and testing. And so we developed, as I say, the simplified additive difference model specifically for this task of Tversky's. And we modeled the overall subjective probability by a linear function of the objective difference level, which ranges from 1 to 4. So A0 and A1 are just the slope and intercept of the linear function. So, and then a logistic function relates the overall subjective difference to the probability of choosing A over B for that particular objective difference level. And if the overall subjective difference is 0, then choice will be, the participant is predicted to be indifferent between A and B. If it's positive, that indicates that the payoff difference outweighs the probability. If the overall subjective difference is negative, then the comparison swings in favor of the better probability. So to just explain that a little bit more, here this is graphs of the subjective differences on each dimension. So on this hypothetical example, the subjective difference for the payoffs we've modeled is a linear function, and that for the probability dimension is a non-linear function. But more importantly, at low differences, the difference is positive because the difference between because the probability subjective difference is less than the payoff one. But as you go from 1 to 4, differences of 1 to 4, at the higher end, the probability difference is higher than the payoff difference, and so that gives you an overall difference. So what we model is the overall difference, which is the difference between the 2 dimension differences. And this is an example. The red here is the case you've just seen, an approximation to it, so that the overall subjective difference is high and it crosses the 0 point between 2 and 3, and it's low at the high differences. And so because it crosses the 0 point within the range 1 to 4, that particular version of the model predicts that weak stochastic transitivity will be violated. It can happen in the other direction, But if in the case of the blue line here, it doesn't cross the function, there's a relationship, but it doesn't switch from positive to negative. It doesn't cross the 0 line. The prediction is that preference will be, that weak stochastic transitivity will be satisfied. So this is how it works with the analysis. This is participant 1 again, and Manos calculated the maximum likelihood estimates of the parameters, and the best fitting model for this data is overall subjective difference 2.5 minus 0.98.
Excuse me, Rob.
Yes.
Can I? We have one clarification question.
Okay.
A few slides ago, I guess. How do you get a non-linear relationship from a model with just a one parameter for intercept and one for slope?
Okay, that's a yes. Okay. In fact, as I did say, it's an approximation to this one. This one is trying to model the general case where dimension differences may be either linear or non-linear. So this example is a non-linear case. If the P line was a straight line, a linear relationship for the probability dimension, but it crosses the other line, that's what is modeled in the other model. So the questioner is correct that there's a discrepancy between this slide and the next one. Okay. So it is.
Thank you.
In the general case, Tversky proved that if for greater than 2 dimensions, if one of the dimension difference functions is nonlinear, then transitivity can be violated. That's what he showed. But in the 2-dimension case, it is possible to get intransitive preferences from this model with 2 straight lines which cross. I hope that clarifies the point. So the best fitting parameters on maximum likelihood estimation were 2.54 minus 0.98 objective dimension. So that means that for pair AB, which are close together, the difference level is 1. The model predicts that the overall subjective difference will be, sorry, I'll keep switching slides. The overall subjective difference will be 1.56. And if applying the logistic function, this leads to a predicted choice proportion for AB of 0.82. And for the pair AC, where the difference level is 2, the overall subjective difference on the model is 0.58 in this case. So the choice proportion is 0.64. For the difference level 3, if A compared to D, it moves to negative. So the predicted choice proportion is in favor of the better probability. It's less than 0.5. And for the greatest difference, the overall subjective difference is strongly negative, leading to 0.2 predicted choice proportion. And as you can see, for this particular case, the observed choice proportions are quite close. And for that participant, for all the 10 choice proportions, you can see as you go along the diagonal, if I can do this without changing slides, it's good fit for the main diagonal, a good fit for the difference 2 diagonal, and for 3 and for 4. So we did that for every participant. We fitted the SAD model and identified cases where intransitive preference was predicted by the model. And we classified them cases according to which model fits best. So the model, the goodness of fit of the model on Manos's program was the -2 log likelihood statistic, and the lower the better the fit. So the SAD model is compared to the unconstrained model, which is the model with no constraints at all, so that the choice proportions, the 10 choice proportions, can take any value, and therefore there are 10 parameters for that unconstrained model. And the likelihood ratio test of whether the SAD model is a good fit is to take the difference between the two -2LL measures, and that is a chi-square measure with degrees of freedom of the difference between the parameters for the two models. So for 8 parameters in that case. So in this case, we can see that the SAD model is a good fit on that likelihood ratio test. Whereas the constant choice probability model assessed against the unconstrained model is a poor fit on a chi-square with 9 degrees of freedom, and although it is better than random choice. And the SAD model is significantly better fit than the constant choice probability model. So that's how we use likelihood ratio tests, testing these nested models. And for all, so this is what we found. Over the 7 studies, there are 129 participants. For 32 of them, the data is unknown, because in the early studies, including Tversky's, only a subset of the data is available. But of those 129, we found that 42 were a good fit, and the SAD model was a good fit. It predicted violation of weak stochastic transitivity, which was observed. Now, we also compared these findings to those of Cavagnaro and Davis-Stober, who looked at the same data, and Brown et al., who looked at the same data from the point of view of transitive models. And they found that 15 of these 42 could actually be accounted for by a transitive model, which means that that data is actually inconclusive, because both transitive and intransitive models can account for the data. But nevertheless, that leaves over 20% of intransitive cases predicted to be intransitive, for which the dimensional model is a good fit. And what I've got here, when I've on this column where it says LS int, that's the model, a cubic model approximating the lexicographic semi-order, which also predicts intransitive preference. So there's just a few of those in that figure. If you look at the data for Tversky, we found that his model, the additive difference model, was predicting intransitive preferences, was a good fit for 5 of his participants, the same 5, I think, as he found violated weak stochastic transitivity. But 2 of those cases are inconclusive, because they can also be accounted for by a transitive model. In Regenwetter's et al. Study, it is true, in fact, that there's only one of Regenwetter's participants for which a transitive model can be rejected. However, we look at it from the dimensional model point of view, and what we see is a replication of Tversky rather than a failure to replicate. We see that 4 participants, including the one I've shown you, had observed violations of weak stochastic transitivity, and the SAD model was a good fit to the data, which is very similar to Tversky's, who's found 5 out of 18 were a good fit. In the later studies by Cavagnaro and Davis-Stober and by Colenso et al., you can see there's rather more cases of intransitive preference for which transitive models can be rejected. So our summary is that for about 30% of participants across all the studies, the SAD model, or a cubic approximation approximating lexicographic semi-order, predicted observed violations of weak stochastic transitivity and was a good fit to the data. In 2/3, there was strong evidence against transitive models, and in these cases, Tversky's original findings of systematic violations of weak stochastic transitivity were replicated and accounted for by dimensional models, but not transitive ones. In the other third of the cases, the evidence supporting the SAD model was inconclusive, as I said. So that's where we got to with our 2020 paper. And if I've got time, I want to go through the remaining issues that we're working on at the moment. Is that okay?
Yes, sure. We have still time.
Good. Okay, so the first issue is which dimension-based model accounts better for the intransitive cases? Is it the simplified additive difference or the stochastic lexicographic semi-order heuristic? So is this important? Well, we think it is, because if the additive difference model offers a better account, then first of all, prospect theory isn't supported by this data, along with many other theories. But more importantly, it implies a significant role for compensatory dimensional processing in choice between simple lotteries, which may generalize to more complex choice situations. And this, I think, is an important aspect of bounded rationality, that we do process things by dimension, and it can lead to intransitive preferences, which I suppose is what Tversky concluded in the first place. But as I say, the compensatory model has never been tested against the heuristic model before, and we're in the process of doing that. I've shown you this before. This is showing that the SAD model predicts participant 1 well, and this is trying to show that if, although we're still in the middle of analysing this, if you get a sudden switch from something like below the threshold 0.75 choice of better payoff to above the threshold a better about a 0.33 choice of the better payoff, then clearly the model doesn't fit as well. The interesting thing is going to be how many cases is the compensatory model significantly better than the heuristic account. The other remaining issues are, does the SAD model predict adherence and violation to the alternative criterion of transitivity, the triangle inequalities condition? And thirdly, can insights from analysing the SAD model inform Kalencha et al.'s findings on the neural signatures of intransitive preferences? I haven't got time to go into the second one, but we're looking at that, and we think it does add some insight into Kalencha's findings. But on whether does the SAD model predict adherence or violation of triangle inequalities? And these are some hypothetical cases showing that it predicts both adherence or violation of triangle inequalities, depending on how steep the function is. So the bottom two both violate predictions of violating weak stochastic transitivity because they cross the 0 point, but the steeper one also violates the triangle inequalities condition. For the two where above, I'm pointing with my finger now, where the subjective differences are higher and both predict satisfying adherence to weak stochastic transitivity. Again, the steeper one predicts violation of triangle inequalities. And on our analysis, which we've just completed, for Tversky's case, out of all the 80 triads, 10 per case, you can see that 22 were observed to violate the TI condition in Tversky's case, and the prediction of the model was correct in 82% of those cases. Similar for observed adherence to the TI condition, and similar again in with Kalencha's data, although the prediction of violation was a little bit lower, and the prediction of those that would adhere to the TI condition was a little bit higher. So looking at it another way, where the SAD model predicts a majority of the triads in a case will violate the TI condition. In Tversky's case, that was 3 cases. The actual number of observed violations is quite high at 6, but where the SAD model predicts adherence to the TI condition, the number of observed violations is much lower at 0.8. So in conclusion, dimensional models predict both transitive and intransitive preferences, and only about 15% of cases overall were not a good fit on this data set. And if decision makers process dimension differences on both payoff and probability dimensions, preference for simple loss rules may be intransitive on either criterion of transitivity, of stochastic transitivity, and 30% of cases were consistent with this with respect to weak stochastic transitivity. And a compensatory dimensional processing model accounts well for most intransitive cases. If only one dimension is processed, preferences will always be transitive and stable, but a substantial proportion of choice patterns of this kind were consistent in our analysis with simple one-dimensional take the best heuristics. Okay, thank you for listening.